We are going to talk today about another way to find maximums and minimums. This section is called Lagrange. That's called Lagrange multipliers and constrained optimization. It's kind of difficult to see what I wrote because this was a long one. But the idea for this section is we're going to find maximums and minimums again, but we're going to have a constraint. Okay, so maybe I have a three-dimensional, and you can look, you probably want to look in your book at the picture. This picture is on page 368. But maybe we have some three-dimensional function, and this dotted line just means it's kind of going behind here. And it definitely has a maximum, doesn't have to have a maximum, but maybe I don't care where the maximum of the whole function is. Maybe I have some sort of constraint, okay, that I have that x and y must follow. So maybe I constrain x and y somehow so that all my x's and y's must lie on this kind of slice of this big function here. So basically what we want to do is we want to maximize this function here subject to this constraint that I'm given with this yellow curve. Okay, so that's the idea today. And we're going to use a process that is called Lagrange multipliers. So let's just kind of jot down this theorem, and you can do this in your book. So I'm just going to kind of do a quick theorem of this. So let's let f of xy be subject to, and then we'll just do two examples and probably call it good, because you can look at the rest of the examples of the book. So subject to the constraint. So this constraint will just be some way that x and y are related. So I'm going to say g of xy, equals 0. But it could be like this example that they give you in the book for this red line, or that's yellow. This is the constraint equation here. But if we can always set it equal to 0 by just bringing that 25 over. So that's why they say it's set equal to 0. Okay, so let's let f of xy be subject to this constraint, g of xy equal to 0, and have a relative max or min at AB. Okay, then there exists, well, I said I was going to do this shorthand, but I'm not. A lambda. Okay, and so this lambda that we're talking about, and that lambda, that's a Greek letter. It's called lambda. This is just going to be a constant. I'm really running out of room today. I don't know why I'm dealing with that. This is a constant such that the partial derivatives, so I'm just going to say the partials of this new function that we are going to define is going to be a function of x, y, and lambda. And this is how we're going to define it. We're going to define it as our function f of xy. That would be like our purple guy here. And then what we're going to do is we're going to add lambda times this g of xy, which is our constraint. Okay, so this is going to be the new function that we're going to define. This is the method of Lagrange multipliers. I know it's a little bit weird, but bear with me. We're going to do a couple of these. So there exists a lambda such that the partials of this function right here all equal 0. At some point A, B, C, where this A and this B again is where this function has a relative max or min. So what that says is if I take the partial of this new function capital F with respect to x, that's going to be 0 evaluated at, right? That evaluated at A, B, and C. Partial of big F with respect to y, and set that equal to 0. And then the partial of this big F with respect to lambda equal to 0. I'm going to find what point makes all of those 0 at once, and that will give me my max or min. So the thing with this is, if you notice, it's not telling us how to find a maximum or minimum. So what I will need to tell you, or what the problem needs to tell you, is does this function have a max or a minimum at this point. So it'll say, or does it have a maximum or minimum period with this constraint? So let's do an example, because that's always the easiest way to just see what we're doing. Okay, let's get a new layer here, and let's do an example. So let's minimize the function. So this function is a function of x and y. And if you think about the function 2xy, it really, I mean, I guess it might have a minimum, but probably not, because we can make this as small as we want. You know, as long as we take numbers x and y that are like really large negatively or something, I could make this function as small as I want. So this function might not have a minimum itself, but it will have a minimum subject. It will have a minimum if I place some restrictions on x and y, subject to the constraint. And the hardest part about these are going to be the algebra. Just like, that's so true in calculus, period. You know, is that the hardest part about calculus really is the algebra. Okay, so what I want to do is the first step is you need to create this new function. Capital F of x, y, and this new constant lambda. Remember, it's f of, I'm just going to write this down again, f of xy plus lambda g of xy. I want to see you guys do this. I want to see you use good notation. You've seen me kind of put that on your homework, I think. You're in Calculus 2 now, so I'm going to start kind of getting on you guys about using good notation, using equal signs, telling me what everything is. I shouldn't have to guess. When I read your work, I shouldn't have to guess what something is. I should know, oh, this is the partial with respect to x. This is the partial with respect to y. Okay, so remember in our last thing that this guy right here, we had g of x, y, and the theorem was equal to 0. So this is why I get the x plus y minus 6. Okay, and let's start taking some partials. So again, I'm going to tell my reader what I am taking the partial of. So let's take the partial of this with respect to x. So if you look at the 2xy, that just becomes 2y. And I want you to kind of think about what would happen with this guy right here. If I took the lambda through, I would get lambda x plus lambda y minus 6 lambda. And remember, we're going to just, lambda is technically a constant, but when I derive, I'm going to derive it like it's a variable. So what would the derivative of this be? Well, the 6 lambda would go to 0. Lambda y would go to 0 because we're deriving with respect to x. And the lambda x, the derivative of that with respect to x would just be lambda. So I'm going to set that equal to 0. I'm going to take the partial with respect to y. Okay, I would get 2x plus, again, if I look here, I would just have a lambda. Set that equal to 0. And then the last thing, now the reason I didn't take the lambda through is because when you take the derivative with respect to lambda, if you notice, this guy just goes to 0, and then I have lambda times all of this is just considered a constant, right? So basically what I get when I take the derivative here, whoops, with respect to lambda is I just get all this function that's being multiplied by lambda. All right, so I hope that makes sense. So what I'm going to do now, and this is usually a good way to do this, not always, because sometimes these can be a little bit tricky, but I'm going to solve these two for lambda. Okay, so if I solve this for lambda, I get that lambda equals a negative 2y and that lambda equals a negative 2x. So that means then, because they both equal lambda, that means negative 2y must equal negative 2x. If I just want to think of this as a simple substitution, I'm going to take this lambda right here, which is equal to negative 2y, and I'm going to substitute it in for that lambda right there. Okay, divide both sides by negative 2. What does that tell me? That tells me that y must equal x. Now I need some way to find y and x, so I'm going to plug it into this equation. Okay, so I'll just let y equal x, so I would get x plus x minus 6 equals 0. So I get 2x equals 6, so I get x equals 3, which means that y must be 3 as well. Okay, and then I can find my lambda if I want to too. I don't really need to though, because I found the point where my minimum is going to occur, okay? And what is my minimum value? Well, I would plug that into my original function, right? Which would be 2 times 3 times 3, which is 18. And here is how I would like you to state your answer. So we can say oh, and I said this was a minimum. Oh man, I am so sorry. This is actually a maximum. Sorry. Ooh, that's bad all the way up at the top here. We want to maximize. Sorry about that. I just looked at my notes and we want to maximize the function. So the maximum, here's how I want you to state your answer of f of xy equaling 2xy subject to, you don't have to put the constraint, but subject to x plus y equals 6 is 18 and occurs at 3, 3. So I need to hear something like that. The maximum of the function subject to this constraint is blah, and where does it occur? At 3, 3. So I need to know those things. I need to know what is the maximum or the minimum, depending on what I tell you, and then where does it occur. Okay, and sentences are great. I will take sentences. I know I'm not an English teacher, but it's important to be able to express what the solution means in mathematics or people don't get it. All right, I want to do just one more, and then I'm going to let you look at the book and kind of look at the examples that you're given. And if you have questions on this stuff, you got to let me know, because I know that sometimes the algebra in this can be kind of tricky. So please let me know if you struggle at all with this. So what I'd like to do now is an example that we've seen before. So consider the production function. And we've kind of seen this actually on your homework. I think it was on 7.1. So the production function f of xy, so this is the Cobb-Douglas again, equals 60x to the 3/4 y to the 1/4. Okay, and where x is units of labor and y is units of capital, so I hope we know that. And then let's suppose, just kind of like we saw in 7.1, that labor costs $100 per unit and capital costs $200 per unit. Okay, assume, now we know what assuming does, but in this case we can do that, that $30,000 is available to spend on costs. I'm not sure I spelled that right. Oh well. All right, so that's my constraint. Assume that $30,000 is available to spend on costs, okay? How many units of labor and capital will maximize production? I just really like this example because it gives you a good example of a real life problem a real life business problem where there is a constraint. And what is our constraint usually? We only have so much money to spend on making whatever we're going to make, right? We only have, maybe $30,000 to invest in creating this product. And that is a real life situation. If I had an unlimited amount of money, then I could probably produce an unlimited amount of units if I wanted to. So let's look at this. So again, we're going to write out our new equation, right? Our new function, which is well, actually, before we do that, let's talk about cost. What would the cost be? Right? What is my constraint here? Sorry about that. I got a little too excited. Let's go back a little bit. So what is my constraint? Well, my constraint is I can spend, if it's $100 per unit of labor, $200 per unit of capital, the most that I can actually spend is $30,000. Remember this cost function from your 7.1 homework. $100 for a unit of labor, $200 per unit of capital, and that better equal 30,000. Okay, so now we can get this new function, which I was so excited about. All right, so f of x, y, and lambda. This would be, remember, little f of x, y plus lambda g of x, y, which in this case is that 60x to the 3/4 y to the 1/4 plus lambda. I'm going to need a little bit more room here. Let me make this a little smaller. Plus lambda times, I'm going to just set that sucker equal to 0. 100x plus 200y, sorry about this, minus 30,000. Okay, so there's my new function, and now I am ready to start taking partial derivatives. Now, the algebra is going to look a little nasty here, but I promise it's going to work out really nice. So let's find, I'm going to do the different notation now just for fun. Big F sub x, so if I take the derivative of this with respect to x, here if I take 3/4 times 60, I get 45. Right, 4 goes into 60 15 times, and 15 times 3. And if I take 1 away, I get a negative 1/4. The y just hangs out there as a 1/4. And then again, if I think of that lambda coming through, these guys here are going to 0. But if I bring that lambda through, the derivative here will just be plus 100 lambda. Set that equal to 0. F sub y, same thing. I'm going to bring the 1/4 down, so that would just be 15. The x just hangs out because it's treated as a constant. I get y to the negative 3/4. And then here I would, if I took that lambda through, I would have plus 200 lambda equals 0. And then the last equation that we need to find for our Lagrange multipliers here is just take the derivative with respect to lambda, and all you're going to get here is this function right there. So 100x plus 200y minus 30,000 equals 0. Okay, so just like before, I'm going to solve these two equations for lambda. So this is going to be a little crazy, but we can do this. So I'm going to get lambda equals, I'm going to subtract that over, and I'm going to divide by 100. Okay. Oh, why do I have? So we're going to be off by a negative here, but that's okay. I think we'll be all right. I should look at my notes before I get a little cocky when I do this. Yeah, let's change this really quick. I'm going to rewrite this. I'm going to set this equal to 0 by actually subtracting the 100x and the 200y. This is just going to be a little bit better for me, because let's think about my maximum amount that I can spend is 30,000, and then I would take away the cost, and that would kind of give me how much I would have left. So I'm sorry about that. So if you guys don't mind, I just want to switch this a little bit. I don't think you don't mind, right? You guys understand. You guys make mistakes sometimes, and I do too. So it's good to see that sometimes, mathematicians make mistakes as well. So I'm sorry about that. I'm going to change that a little bit just so that we get some nicer numbers when we deal, then when we come through and deal with this, we won't be getting negatives and wondering why that happened. So let me go through really quick. Now, not that we couldn't do it that way. We could. But if I can have some hindsight or some foresight here into seeing that I want that 30,000 and then I'm reducing it by this amount once I spend the money, that makes a little bit more sense. So this will be negative and this will be positive. Okay, so thanks for understanding. I'm getting a little confused here by all this. So I'm going to just draw a light line right here. Realize that was kind of my setup problem. And now we're ready to solve this equation right here for lambda. So I'm going to add the 100 lambda over and then divide both sides by 100. So 45 divided by 100 is the same as 9 divided by 20. Just divide each one by 45, or 5, excuse me. And then when you bring, so I just divided by that 100, so I still have this x to the negative 1/4 y to the 1/4, okay? And then same thing here, I'm going to do the lambda. I would add the 200 lambda to both sides, if you can kind of see that. So I would get the 200 lambda over here, and then divide both sides by 200. That's probably the easiest way to solve for lambda, is just to move that 1. And if you simplify that fraction, you get 3/40, and you still have the x to the 3/4, y to the -3/4. Okay, so I know that's a little crazy, but now again I'm going to do the trick that I did before. I'm going to set these two equal to each other because they both equal lambda. So I have 9/20 x. Now I know this looks gross, but actually it's going to be pretty great. I'm going to show you what happens with our exponents here. So I have x to the 3/4, y to the -3/4. So watch what I'm going to do first. I'm going to get rid of some of these negative exponents right here. They're really bringing me down. So I'm going to multiply both sides by x to the 1/4. Okay, so I'm going to do that first. So what happened? Why did I do that? Because when I add these exponents, then these guys are going to cancel, right? 1/4 minus 1/4 is 0. So I have 0 x's. So I have 9/20 y to the 1/4 equals, and then look at what happens here when I combine these two. Remember, you add exponents, so 3/4 plus 1/4 is 1. So that's so great. So I just get x right here. Now I still have this y to the -3/4, but I'm going to do the same trick. I'm going to multiply both sides by y to the 3/4. And I think you can see what's going to happen. So again, what happens here is I have y to the -3/4, y to the 3/4. Those cancel. Add exponents, right? We add exponents. 3/4 plus 1/4 is 1. So I just get y. So I get 9/20 y equals 3/40 x, okay? And then we can just solve for one or the other. I can solve for y by just multiplying both sides by 29ths. Okay, and what do we get y to be? It looks like y equals, if I simplify this a little bit, I think I get 1/6. Okay, I'll let you verify that, but 20 goes into 40 2 times, and 3 goes into 9 3 times, so I think I get 1/6. Whew! That was some fun algebra, people. That was a good time. Now what am I going to do with this? I'm going to take this fact right here and plug it into this equation, because that is the other equation I have that relates x and y. So I'm going to leave the 100x minus 200 times y, which I found was 1/6 of x. And then I'm going to move that 30,000 over, and I'm going to get my negative correct there. So let's see what we get here. So we get 100x, right? If I simplify that, that's, oh, that should be a -100. Sorry, negative right there. Minus 100 x equals a -30,000. And I could get rid of all the negatives, multiply the whole thing by a negative. And we get 400 x equals 30,000. Again, I just multiplied through by a -1. And so what if you solve for x? This is pretty great because you get x equals 225. And then if you solve for y, you just take a sixth of that, right? You get y to be 37.5. So that was a lot of work, but it wasn't too bad. I mean, really, the easy is so true in calculus. The easy part was the calculus. The hard part was the algebra. And then, of course, I would write my answer in a nice thing. I would say something like, you know, we would get maximum production. We can maximize production when we have 225 units of labor and 37.5 units of capital. Okay, so that's kind of what that means. I hope that makes sense. Please look at the other examples in the book. That was a good example to show you that's applied, but you'll also want to look through the other examples, especially the examples that involve different ways that we can solve for, you know, that x, y, and that lambda. All right, as usual, let me know if you have any questions.